All right, the final presentation in this session will be by Hadar on scalable spreadsheet-driven end-user applications with incremental computation.
Good morning. I'm Sean, and this is the work I've done with Shachar Itzhaky. We are from the Technion, Israel Institute of Technology. So, as you all know, spreadsheets are electronic grids, and they are used to store data and compute data out of the stored data. Each cell in the spreadsheet is either a data cell or it's a formula cell that computes new data out of the stored data. Spreadsheets are visual and reactive, so they are very useful by both programmers and non-programmers, very widely in applications like Microsoft Excel, Google Sheets, Apple Numbers, and so on. This is an example of a spreadsheet. So as you can see, we have years, quarters, and for each quarter we have a transaction, either incoming or outgoing. And for each quarter we sum up the revenues and the expenses and the net income, and then we have the sum for each year of the quarters. When you change one cell in the spreadsheet, it can initiate many other changes, because one change leads to other changes of cells that depend on it, and other cells that depend on those cells, and so on. And when the spreadsheets get bigger and bigger, this is a big challenge, how to do it efficiently. There are two naive solutions for that. One is to recompute the whole spreadsheet every time, but that will obviously take a huge amount of time for big spreadsheets. Another naive solution is to make a graph of all the cells, and for each two cells keep an edge if they are dependent on each other. But that graph would be huge, and it is very hard to maintain. But as you can see in the example, when adding a transaction or removing a transaction or updating a transaction, the quarters sum and the year sums need to be updated, but the other quarters and the other years don't need to be updated. We don't need to recompute them. Furthermore, we don't need to recompute the entire sum. We just need to recompute the delta, and after by the transaction that was changed, and by that delta update to the new sum. This is a spreadsheet in a framework called Spalier. Spalier is an object-oriented spreadsheet programming environment. So each cell is in an object, and the object has a hierarchy, and each object has a contained objects and fields. So there is a schema which defines the hierarchy and the fields. Our goal in the research was to look for a set, as small as possible, of cells that when we update one cell, these cells need to be updated and no other cells. And then we used the former data to shorten the data computation even more and to make it shorter. We created an algorithm for it, which I will present, and implemented it in Spalier using the schematic structure of Spalier. Our algorithm comprises of two phases. The first is the offline phase, which can be thought of as the compilation time. So before the user uses the spreadsheet for updates, we analyze the structure of the spreadsheet and create data structure that will help us later do fast updates. And then the online phase, which is the running time, can be thought of. It's whenever the spreadsheet is updated. When the user updates the spreadsheet, we use the data structure from the offline phase. In the offline phase, we create a graph of the columns, not all the cells, but only the columns. For columns C1 and C2, there is an edge from C1 to C2. If a cell in C2, some cell in C2, may depend on cells in C1. So if C2 is somehow dependent on C1, we have an edge. But a cell in C2 doesn't necessarily depend on all the cells on C1, but only on some of them. For that, we create three dependencies type, three edges type. The first is horizontal, which means a cell in C2 depends on a cell in C1 only in the same row. Then we have the incremental computation, the incremental dependency, which means that each cell in C2 depends on a set of cells on C1. That's the most complicated type of formulas. It's formulas like filters, aggregations, sums, averages, and such. And the third type is the arbitrary type, which means we don't have enough information in the offline phase. And then we say that every cell in C2 depends on all the cells on C1, which is a fallback to the baseline full recompute. Let's focus on the incremental dependencies. So each incremental formula has this general structure. We take this, which is the object where the formula exists, and then we go with the function q from x, from this to x, which is a set of cells, and on each of them we compute a predicate, that is the filter, and then for all of the x's that pass the predicate, we compute some arg function, and then we aggregate all of those by sum or any other operator. Let's see an example. So this is a spreadsheet of classes and students in the class. Each student has a grade, and each class has an average and STDF. STDF is our function phi, is our formula. AVG can be computed automatically from the grades, but for this example, to make it more interesting, the AVG is manual. It's a data cell and not a formula cell. So the STDR, the phi, is we take all the students of the class. This is class because phi is in class. So we take all the students. For each student that has a grade of 55 or more, that's the filter, we compute the arg, which is x point grade minus x point class point AVG squared. And this STDR is dependent on two things which can be changed, and if they are changed, we need to update STDR. One case is that a grade of some student is updated, and the second case is that an AVG of some class is updated. We identify the read sites. Read sites are areas of the formula that refer to modified fields. So each read site, which you call PI, takes us from X, which is the set of cells, to someone, to Y, which is the modified field. So in this example, the X for each PI is student, because the set of cells that we sum on is students, and each PI takes us from student to Y. And what is Y? That depends on which object was modified. So in the first case, a grade is changed. So Y is student because grade is contained in the student. And the grade is found twice in our example. Once in the arg part, in the left part, and once in the right part, in the predicate. So in this case, we have two read sites for grade, which are both the identity functions, with p of x to x. In the second case, some AVG is changed, and so if AVG is in class, so y is class, and AVG is found once in this formula, in the arg part. So in that case, the read site will take us from x to x point class, because it takes us from the student to the student point class. After we have the after we have the read sites, we can find the affected objects by them. So for each read site pi and the modified object y, we compute e of y, which is the set of cells that may be affected because of modifying y. That's all the objects in O that Q of O intersect with the pi inverse of y. Because there is some cell which is both in Q of O in the sum and in the inverse of the read site. Therefore, EI of y is Q inverse of pi inverse of y, and then we unify on all of them and get EY, which is a set of all objects that may be need to be recomputed, may be changed because of modifying y in respect to our formula phi. Let's see it in the example. So we did have Q, which is the set of cells. Each Q takes us from a class to all the students. So Q inverse of x is x point class. In the first case, a grade of some student is modified, and therefore, as we computed before, the PIs were the identity, so the inverses of them are also the identity in the left side. So P1 inverse and P2 inverse of y is y. Therefore, E1 of y and E2 of y are both Q inverse of P inverse of y, which is y point class. And therefore, EY, which is the unifying of them, is y point class. That means that when a grade of some student is modified, we get the class that contains that student, and that class needs to be is affected, and its STDF needs to be recomputed. In the second case, we have AVG of some class that is modified. Therefore, PI was y point class, so P1 inverse is y point student. E1 of y is Q inverse of P inverse of y, which take us back to y. And therefore, EY is y. That means that when an AVG of some class is modified, this class is affected, but only this class. No other classes are affected. So when an AVG of some class is changed, we need to recompute the STDF of this class. Then we have the incremental change. After we find the EY, of y, which is the set of cells that must be updated because of modifying y, we don't need to recompute the sum again, necessarily, but we do need to only recompute the items in the cells that changed and update the sum by the delta. So we check for each predicate if it's changed, and if it's changed or the arg is changed, we recompute them, but we don't recompute the whole sum again. So that is the algorithm of the offline phase. We check for each two columns that may depend on each other. We take phi, which is the sum, or any other formula. We compute the read sites of this formula. If all the read sites are horizontal, which means they are all in the same line and don't go to other lines, then we say this dependency is horizontal dependency. If it's an aggregation, like filter, sum, etc., then we say this is an incremental computation. We do need that the Q and PIs are invertible. And if they are invertible, you can say this is incremental dependency. And in the other cases, we say this is an arbitrary dependency. In the online phase, we get a set M of cells that were changed. And for each M, we check the columns of M. For each cell in M, in the set M, we check which columns they are found in. And for each column, we use the graph to get the columns that depend on that columns and check the type of dependency. If it's an incremental dependency, we compute E by the data that we stored in the offline phase and get E, which is the set of cells that need to be recomputed. And because it's an incremental dependency, we can recompute them by the delta. If it's an horizontal dependency, we recompute those cells that we get from the read sites. And if it's an arbitrary dependency, then we recompute all the cells in that column. After we recompute all the cells, we make them the new M, because after we update those cells, there are other cells that are dependent by them. So this is the new M, and then we do this iteratively until M is empty. In the empirical evaluation, we wanted to check how much time we save by our algorithm. So we created a benchmark of spreadsheets. We have 6,215 spreadsheets of 5 schemas with varying sizes and data. And we tested 4 modes of operations on these spreadsheets. The first 2 are the naive solutions. The first one is recompute the spreadsheet after each update. The second mode of operation is a full graph of all the cells and their dependencies. The 3 and 4 is our solution. 3 is our solution, but without the incremental change, without the delta. And number 4 is the full solution with the delta. So these are the results of horizontal formulas. In the x-axis, this is the size of the spreadsheets, the number of the objects. And in the y-axis, this is the running time of updating a set of cells. We can see that mode 1, the recomputation of all the cells every time is much slower than the other modes. We can also see that modes 3 and 4 are quite same, because the difference of them is the delta computation, but it doesn't affect here, because here we have only horizontal formulas, and the delta is affecting when we have incremental computations, sums. So here we added incremental formulas, and then you can see that mode 3 is slower than mode 4. That means that the delta computation saves us some time. You can also see that mode 2, the graph of all cells, is also very good in running time. But in the next slide, we can see this is the memory consumption. In the x-axis, you can see the spreadsheet size, and in the y-axis, the memory of the data structure. So we can see that mode 2 is much more taking much more memory than our solution. So that's the main advantage of it. So to sum up, spreadsheets applications are very useful, and they need to deal with a huge amount of data. which is growing up. In the presence of this challenge, updating the spreadsheet every time needs to be done efficiently, and the naive solutions are not good enough because they are either very slow or taking too much memory. So we presented a new solution for this problem by taking advantage of a schematic structure of the spreadsheet, in Spalier it as the structure, but for every spreadsheet with a structure, this solution can be applied. We focused on aggregation formulas and created a data structure in the offline phase, and then used it in the online phase to recompute the necessary fields more efficiently. Questions?
Question in the back.
Thank you very much. I have two questions. So the first is, in incremental computing, you often have this problem with granularity, right? Where you have these two extremes, right? Recomputing everything is like granularity, where everything is one unit that can change only at once. And if you have a cell graph, I think you called it, where it's very fine-grained. So isn't there something in between? You present one solution, but like a naive one where just like somehow figure out, oh, there are cells that happen to change together a lot, and just treat them as one thing that can be updated. Like it's full recompute, but locally. Have you kind of thought about what is the right granularity for spreadsheets?
Yes, that's an option, but that requires to analyze the usage of the spreadsheet to see which cells are updates, have a lot of updates, and get to. You can take the full graph of cells and and only save small parts of it. That's a good optimization, but I'm not sure it will do well for any kind of spreadsheet. But it's a nice option to investigate for further research. Yes.
Okay, and the other question I have is, like I'm lucky enough not to use spreadsheets a lot, but when I do, I often have to insert rows or columns, right? And as a consequence of that, the definition of cells changes. Like there's a sum over a range of things, and then Excel is smart enough that, you know, I'm inserting a row, so probably now I mean the sum from, you know, this row as well. So how do you handle this kind of change? It's a different kind of change, right? Not the data in the cell, but actually the formula is changing.
Yes, but if the spreadsheet is a schematic, then the sum is defined not for a range of cells, but just to be all the cells in the formula. So for schematic spreadsheets, in the syntax of the formula allows it to just contain all, and when we add some row or remove a row, then it's already included in the original formula, because the formula just says take the whole row.
So perhaps related to those questions, can you say exactly when this static compile time step is being executed, and something about the overhead that it causes?
The time measurements were done actually on this computer. So we created a benchmark automatically with a script that generates a lot of spreadsheets of different types, and then created a set of cells that are changed, and measure the time that it takes to update the spreadsheet. Is that what you meant?
Yeah, so what is the overhead specifically of the compile time step compared to the incremental recomputation? Is that something that you analyzed?
I don't have it, but it was quite a short time, especially when there are when the most important is that it's a static time. It's not growing when the spreadsheet is getting bigger. But I don't have the amount of time, but it's quite short.
Thank you for your paper. I'm glad some people are still doing basic spreadsheet research. You said you focused on aggregation formulas. Do you think that you would still get the same result as far as the memory optimization between the traditional dependency graph and your approach if you just had an arbitrary set of spreadsheet formulas, not just aggregation formulas?
Arbitrary formulas are our fallback when we don't have enough time, enough information in the offline phase. It does better than recompute the whole spreadsheet, because we just recompute this column, the dependent column. That's also that can be also a good start to analyze the columns dependent, but not further save any data. So we can recompute only the relevant columns and not all the columns. So this is actually a first step, and the second step is analyzing the formulas in such a way that we don't need to recompute the full column when possible.
No question?
So I might have missed this. It seems like the compilation phase, the collection of the graph, didn't seem fully precise. I wonder, I guess my first question on it is if that is because of the type of data you receive, or that you're able to collect from the spreadsheet that you're working with. And second part of that is if there are improvements that could be made or obtained from that collection of data that would improve the speed or precision of your algorithm.
Yes, if we have more data on the spreadsheet on the specific spreadsheet, we can have specific adaptations for maybe other types of columns that fall to the arbitrary type, but we can adapt specific handlers for them for the specific spreadsheet. Or if we can see that some kind of formula is used a lot and we don't cover it and it falls to the arbitrary part, then we may have in the further research find some shortage for a way to shorten this computation. So that's a nice plan for the research to cover it to more kinds of formulas.
Thank you.
All right, let's thank the speaker again.
Thank you.